Ladies and gentlemen, good afternoon. Let's continue with chapter 11 on heat exchangers. We are making use of the book of Cengel and Ghajar. Yesterday I've started by giving an introduction of the different types of heat exchangers, and then we've just started with the concept of the overall heat transfer coefficient U. What is the idea of getting U? The idea is to make things simpler. The idea is to have an heat exchanger and to say to an engineer or somebody the overall heat transfer coefficient, this is the value. And if you've got the value, you can calculate the heat transfer rate, or if you've got the heat transfer rate, you can calculate the delta T's without in detail needing to go into the heat exchanger and all the detail and look at what is the heat transfer coefficient on the inside stream and the heat transfer coefficient on the outside stream. So that is the idea with the generation of the overall heat transfer coefficient. In terms of the deriving of it, or where does it come from? It comes from the total resistance. It can be written as the resistance of the inside heat transfer coefficient, the resistance of the wall, and the resistance of the outside heat transfer coefficient. In general, you can show that U multiplied by the area on the inside is equal to U multiplied by the area on the outside. Normally, these two are not the same, except if that area and that area is the same. Then the two heat transfer coefficients would be the same. But in general, if you get, or if somebody gives you the overall heat transfer coefficient of a heat exchanger, you should ask, is it based on the inside area or the outside area? Okay, it's very important to always remember that. Now, in terms of the resistance of the wall, normally we are looking at two different types of walls in heat exchangers. The one where you've got typically a tube in tube, that is the inner wall, that is the inner diameter, and that is the outside diameter, and the heat transfer occurs over that wall. The other type is a wall like this. This you will typically get in a plate heat exchanger, and there the resistance would be determined by the thickness divided by the thermal conductivity of the wall multiplied by the area of the wall. That is the general equations. Now, what I specifically want to focus on in this chapter is that you shouldn't just always close your eyes and go through all the calculations and end up with an answer. Because if you do that, then you are going to miss very important things. As an engineer, you're going to make the wrong decisions and you're going to make the wrong choices. You really need to understand what is actually going on, let's call it, on the inside of the heat exchanger, specifically in terms of all the different resistance terms. And I'm going to focus on that now. Let's suppose we've got an if. If the wall thickness is small, and that is usually the case, but not always. So usually it is the case, but not always. Then it means that if you go and look at this, if this is thin, it means that that diameter and that diameter, the ratio of it will approximately equal to 1. The ln of 1 is 0. Okay, so it would mean that the resistance of the wall would normally be equal to 0. The same for this type of wall. If X is very thin, then the resistance over the wall is also very thin. Secondly, so that's the first condition. The second condition is K is high. With that, I indicate a high value. Typically, let's suppose it's copper, then it's 280, something like that. And again, now you're going to have the ln of something, which is going to be ln of approximately 1. It's a small number, and you divide by a high number. So again, the resistance of the wall would be equal to 0. And again, here also, if the thermal conductivity is very high, then the resistance of this wall is equal to 0. These days there are lots of plastic heat exchangers in many radiators of cars are being made from plastic. Now again, in their cases, the resistance of the wall is also equal to almost zero. Not maybe because the thermal conductivity is high, because the thermal conductivity of plastic is lower, but because the walls are so thin. If the walls are so very, very thin, then the resistance of the wall doesn't play a role. Okay. Now the third case is if the inside area is approximately equal to the outside area. And again, this is for the thin case. Thin heat exchangers, thin walls. Then in many cases you're going to get these three conditions together. If you have these three conditions, and we look now at this equation, it means that area is equal to that area, do you see? And that area is obviously equal to that one. So it means that 1 divided by the overall heat transfer coefficient is then equal to 1 divided by the heat transfer coefficient on the inside plus 1 divided by the heat transfer coefficient on the outside. So you make things really very simple. However, take note, to do that is a judgment call. You can't just go and do it all the time. And I'm going to show you typical examples of how you can do that. And if that is the case, then of course the U in general is equal to U on the inside is equal to the U on the outside. So it's a very simple case. Now let's look further at what can also happen or happens in many cases. If we have now this case of the two heat transfer coefficients that determine the overall heat transfer coefficient, then we can typically have, if we look at the two resistances, if that is now the inside temperature and that is the outside temperature. Okay, there should be the resistance of the wall, but we've said it is very small, it is negligible. So what we normally have in many cases, not always, is typically, let's suppose this heat transfer coefficient is equal to 3 and this heat transfer coefficient is equal to 1,000. If you as an engineer look at that, then it is something that is very important, because it would mean that this resistance is equal to 1 divided by the heat transfer coefficient on the inside and the area on the inside, and this one will be equal to 1 divided by the heat transfer coefficient on the outside and the area on the outside. So if we now look at this case that we've discussed, thin wall, high thermal conductivity, then it means 1 divided by U would be equal to 1 divided by the inside heat transfer coefficient plus 1 divided by the outside heat transfer coefficient. Okay. Now if you see that, you should already see the red lights. Because what does it tell us? It tells us that this problem is being influenced the most by that value and not by that value. So if you actually now go and calculate the overall heat transfer coefficient U, then it is equal to 2.99 watts per square meter degree Celsius. It therefore means that the answer is actually this value. I get 2.99, but it's actually 3. Thus, if you have a case like this, and you can enhance the heat transfer, and normally there are two methods that you can use, well, at least two methods that you can use to enhance the heat transfer of a heat exchanger like this. The one is you can change the surface area so that there's more surface area, and the other possibility is you put on fins, and fins also actually increases the surface area. This would mean that if you go and put on fins on that side, you're just wasting money. It's not going to help anything. If you're going to increase that value to 2,000 or 10,000, the answer is still going to be approximately 3. You see that? So it's a very important thing to realize. Let's look at the case where we now have the opposite, and that is, again, if the inside area is approximately equal to the outside area, and again K is very high, and we have the case of a heat exchanger, something like that. The heat transfer coefficient on the inside is 5,000. The heat transfer coefficient on the outside is 10. Again, you can do it. You can say 1 divided by the overall heat transfer coefficient is equal to 1 divided by 5,000. Okay, that resistance is equal to 0 because areas is equal to 0, thin areas, K is very high. 1 divided by 1 divided by 10. So if you go and calculate the overall heat transfer coefficient, it is equal to 9.98 watts per square meter degree Celsius. Again, this answer is being determined by that value. The other heat transfer coefficient doesn't play a role. It doesn't contribute to the total resistance. Okay. Now typically these are the ideal cases if you've got a case like this where the heat transfer coefficient is very low and you want to enhance the heat transfer, you put on fins. So if you're going to put on fins, then we're going to say that the surface area is equal to the total surface area is equal to the area of the fins plus the area of the unfinned area. Okay. So if you have fins typically like this, it's not good to have such thick fins, but I'm just trying to show the principle. Let me use 2 different colors. Pink. Okay. So the unfinned area would be equal to that area plus that area plus that area plus that area, all that areas. So that would be the area unfinned. And you need to sum them, of course. You have to add them together. Okay. Then the finned area would be the area of the fins. So all that area is there. Of course, you would sum them, and they are known as the finned area. Now this equation of AS, which can be written like that, can at the end be written as the efficiency of the fin multiplied by the area of the fin plus the area unfinned. And this is then relates to the short fin, okay. So for the short fin, the efficiency is equal to 1, and that is the isothermal case. You've done that in chapter 3 in your textbook. So it doesn't mean this efficiency is always equal to 1. In some cases it will not. Okay. So you can enhance the heat transfer area a lot and therefore reduce this resistance a lot by adding fins. So that is typically, you go and add the fins on the side with the lowest heat transfer coefficient. Otherwise you just waste your money. It doesn't help anything. The other thing that we need to take into consideration when we look at the overall heat transfer coefficient is at fouling. Now the fouling is going to be written as 1 divided by the overall heat transfer coefficient multiplied by the surface area is equal to 1 divided U on the inside, area on the inside, equal to 1 divided by the U on the outside, the area on the outside is equal to the total resistance. So we do nothing there. However, the total resistance, which is equal to 1 divided by the heat transfer coefficient, the inside area on the inside, what we now do is we add the fouling there. And the fouling can be written as the fouling on the inside multiplied by the area on the inside plus the resistance of the wall plus 1 divided by the heat transfer coefficient on the outside, area on the outside, plus the fouling on the outside divided by the area on the outside. Thus, if we've got a case typically like this, that is the area on the inside, that is the area on the outside. This might be the fouling on the inside, so that can be written as RF, the fouling on the inside, and that can be the fouling here on the outside, RF0, and the values can be obtained typically in table 1.1 for different types of heat exchangers. Oh, sorry, no, those are the overall U values. There they are, in table 11.2. There we can see typical fouling values for different types of heat exchangers. For distilled water, for example, below 50 degrees Celsius, the value would be approximately 0.0001. For above 50 degrees Celsius, you can see approximately 50 degrees Celsius plays a big role. Then the overall fouling would typically double. And for air, it is approximately 0.0004. Let's start with doing some examples so that we can see how we should apply the theory that we've done up to now. And we start with example 11.1 of a tube-in-tube heat exchanger. So that is the one tube, and we've got water flowing through this heat exchanger like that, in that direction. It's a counterflow heat exchanger. And normally, this is just for this specific example to show a point, the average temperature of the hot fluid, which is oil, is given as 80 degrees Celsius. Okay. And the average temperature of the water is equal to 45 degrees Celsius. That diameter is equal to 20, and that diameter is equal to 30 millimeters. Inside tube, 20 millimeters, annulus, 30 millimeters. They do not give the thicknesses of the tube, so we can say it is very thin. And for the water, the mass flow rate was 0.5 kilograms per second. And for the oil, the mass flow rate is 0.8 kilograms per second. Okay. Now normally in tests and exams, in practice, you will have the inlet temperatures and the outlet temperatures. And you can use that, of course, to get the bulk temperature. Typically this average temperature, and that is where you're going to get the properties. But the question is to determine then the overall heat transfer coefficient of this heat exchanger. The overall heat transfer coefficient. Okay. So let's look at the properties of the oil. and that is at 80 degrees Celsius. You can get the properties in table A13. The density of the oil is equal to 852 kilograms per cubic meter. The Prandtl number is equal to 499.3. The thermal conductivity K is equal to 0.138 watts per meter Kelvin. The kinematic viscosity is equal to 3.794 multiplied by 10 to the minus 5 square meters per second. Okay, that is for the oil. And for the water, at a temperature 45 degrees Celsius and table A9 in your textbook. A9, you can go and get all the properties there. Water, 45 degrees Celsius, table A9. The density is equal to 990.1 kilograms per cubic meter. The Prandtl number is equal to 3.91. The thermal conductivity K is equal to 0.637 watts per meter Kelvin. The kinematic viscosity is equal to 0.602 multiplied by 10 to the minus 6 square meters per second. The properties of the two fluids. Okay, now we've been asked to determine the overall heat transfer coefficient. If we just look at this, we can see that one of the critical things that we need is to get the heat transfer coefficient on the inside, to get the heat transfer coefficient on the outside. So, to get the heat transfer coefficient on the inside, we need the Reynolds number. We've got the Prandtl number. Once we've got the Reynolds number, depending if it's laminar or turbulent, for the inner tube, we can select the appropriate equation from the chapter on internal forced convection, and for this case we need it for the annulus. But if you look at it, you'll see that we're going to use approximately the same procedure for both of them. So we start with the mass flow rate, which is equal to rho AV. The mass flow rate is given as 0.8, it's equal to the density is 852. The cross-sectional area of the tube is pi divided by 4. 0.030 minus 0.020 square. So this is the annulus. Remember, this is the oil is flowing through there. Okay. And the hydraulic diameter of, let's call it the hydraulic diameter of the annulus, is equal to the outer diameter minus the inner diameter. Okay, but that is the cross-sectional area multiplied by the velocity v. So from this we can get that the velocity in the annulus is equal to 2.39 meters per second. The velocity of the oil in the annulus. Once we've got the velocity, we can calculate the Reynolds number, which is going to be the velocity multiplied by the hydraulic diameter for the annulus divided by the kinematic viscosity. So on this side we're doing the oil. So the Reynolds number in the annulus is then equal to the velocity, which is 2.39, the hydraulic diameter, which is 0.1, divided by the viscosity 3.794 multiplied by 10 to the minus 5, and that would give us a Reynolds number of 630. The Reynolds number is low. It is low enough so that we know the flow is laminar. We've got laminar flow. And in table 8.4 in your textbook, in table 11.3, Let me check in table 11.3. Unfortunately, I don't have it here, but if you go and look in table 11.3 in your textbook, there are a table from Case and Perkins in which they say that if you've got the diameter of the outside divided by, inside diameter divided by the outside diameter, which is equal to 0.02 divided by equal to 0.03, which is equal to 0.667. If you use that for the case where you've got an annulus, and take note, that is the Nusselt number on the inner tube, and that is the Nusselt number on the outer tube. For that case, the Nusselt number on the inside is equal to 5.45. 5.45. So the Nusselt number is then equal to the heat transfer coefficient, the outside, the diameter, divided by the thermal conductivity. Nusselt number is 5.45, is equal to the heat transfer coefficient. The hydraulic diameter is 0.1 divided by the thermal conductivity, 0.138, and that gives us a heat transfer coefficient of 75.2 watts per square meter degree Celsius. Yep.
Why did you find the heat transfer coefficient on the outside of the inside when you found the Nusselt number on the inside?
Yeah, I know it becomes a little bit confusing now in terms of the nomenclature. Remember, we are working with a fluid going through there. Okay, and the heat transfer rate is over that wall. Okay, so the sketch referred to that as the inside, where the rest of our nomenclature would say the inside is on that side. So it is just a nomenclature thing now in terms of what you will see in the table. In the table, you need to select which one of these Nusselt numbers you're going to use. So you need to use that one because we are interested in the heat transfer over that one. We are not interested in the heat transfer over that surface area there. Okay? So from that table, you can get that Nusselt number is 5.45. It's equal to the heat transfer coefficient, but we are busy with this, so we work with the hydraulic diameter, 0.1, divided by the thermal conductivity. To answer your question? Okay. Right. So that is now for the oil side. Let's look at the water side. For the water side, the mass flow rate on the inside is equal to rho AV. Okay. The mass flow rate is equal to 0.5. I'm not going to write in all the values there for you. The velocity on the inside, from it you can calculate the velocity on the inside is 1.61 meters per second. The Reynolds number on the inside is equal to the velocity multiplied by the diameter divided by the by the dynamic viscosity, and that is going to be 53,490. Okay. Turbulent. There are 4 equations that you can use, from the most simplest up to the Glinsky equation. I typically prefer to use the simplest ones, and that is equal to 0.023 Reynolds to the 0.8 Prandtl can be 0.3 or 0.4. Because the water is being heated, the value is equal to 0.4. If you go and do the substitution of the Reynolds number and the Prandtl number is equal to 3.91. The Reynolds number, there it is. You can just put it into the equation. The Nusselt number is 240.6. If we use that to determine the heat transfer coefficient is 7,603 watts per square meter degree Celsius. Right, as I've asked you many times, and I'm going to ask you that all the time in this chapter, is please just do not go through all the calculations. Look at all the values and evaluate the problem to understand where the challenge is. So if we look at, excuse me, the case now of calculating the overall heat transfer coefficient, which is 1 divided by the overall heat transfer coefficient U multiplied by the surface area, is equal to 1 divided by, you can write it like that, okay, which is then equal to 1 divided by the heat transfer coefficient area on the inside plus the resistance of the wall, plus 1 divided by the heat transfer coefficient on the outside, the area on the outside. I didn't add the fouling terms because they didn't say anything about fouling. I'm not going to make my life unnecessarily complicated. So, coming back to the problem, they didn't give the thickness of this wall. And if they don't give it, then we assume it is very thin. Okay. So if it is very thin, then it means the inside area is equal to the outside area. Take note, the inside area, we refer to that area there, of that wall and that area. Okay, so we are not referring to that area of the annulus because the heat transfer occurs over that wall. That is the resistance of the wall. Now, if that is so, then it means 1 divided by the overall heat transfer coefficient is equal to 1 divided by the heat transfer coefficient on the inside plus 1 divided by the heat transfer coefficient on the outside. The heat transfer coefficient on the inside we have determined to be equal to 7,663. The heat transfer coefficient on the outside, on the oil side, is 75.2. So, if you look at that, you can see that most of the resistance is being determined by that term there. That term is about 10 times more than that term. So, if you go and calculate the overall heat transfer coefficient, then the correct answer would be 74.5 watts per square meter degree Celsius. Okay. So just schematically, that resistance there is very small. There's a resistance there, and then we've got this resistance which is about 10 times larger than that one. So this resistance is equal to 1 divided by 75.2. That resistance is 1 divided by 7,663. So this is our problem. That one is negligible, that one there, and you can see the answer, 74.5, is almost the same as that of the transfer coefficient on the outside. Okay. So, it means that if you've done many of these calculations of heat exchangers, and you've developed a little bit of experience, then you can make life very easy for yourself by looking at the different resistance terms, and from there actually have a very good idea what the overall heat transfer coefficient will be and how to correct the situation to increase the efficiency of a heat exchanger. Let's look at another example, example 11.2. With this example, again a tube-in-tube heat exchanger. This is a hot fluid. It's a counterflow heat exchanger. And there's the cold fluid. The tube on the inside is from stainless steel one, and the K value is equal to 15.1 watts per meter Kelvin. The tube diameter looks like this. That is the inner tube, and that is the outer tube. Okay. This inside tube is 15 millimeters. The outside diameter is 19 millimeters. Okay. 15 for the inner tube. The inner tube outer diameter is 19, and that diameter of the annulus is equal to 32. Okay. Now you will see in many cases when the annulus dimensions are given, only this dimension is given, because that dimension doesn't really play a role. So again, for this problem, we have to calculate the overall heat transfer coefficient, the heat transfer coefficient on the inside, and the overall heat transfer coefficient on the outside. Oh, and we've got fouling. So fouling is also given for us. RFI is equal to 0.0004 square meters Kelvin per watt, and on the outside surface area it is equal to 0.000 watts, 0.001 watts, 0.001 square meters Kelvin divided by watts. That is the units typically of the resistance terms. And looking back there on the first board that we've started with, again the total resistance, we can see it is equal to the sum of the three resistance terms, and then here we've added the effect of the fouling. So the fouling on the inside is just RFI divided by the area on the inside, and the outside fouling is RF0 divided by the area on the outside. So if we look at the fouling, then in this case, for the inside and the outside, the only fouling that plays a role here is this fouling. We call that RFI on the inside, and then the fouling on that side there, RF0. So fouling doesn't really play a role here because there's no heat transfer here. Obviously, if there's lots of fouling, it will influence the velocity here. The average velocity would actually increase and the pressure drop will increase. Okay. So in terms of getting the total resistance is 1 divided by U divided by the surface area. And we can write it as 1 divided by the heat transfer coefficient on the inside, area on the inside, plus RF on the inside divided by the area on the inside, plus the resistance of the wall. Let me write it rather down. The resistance of the wall, which is the limb of the outside diameter divided by the inner diameter divided by 2 pi KL. And then the heat transfer coefficient on the outside plus the resistance of the fouling on the outside. There's the total resistance term. The area on the inside is equal to pi, the diameter on the inside multiplied by the length. They didn't give us the length, but we just use 1 meters. So the area is equal to pi multiplied by the diameter. Inner diameter is 15 divided by the length 1, and that would give us an inside area of 0.0471 square meters. The area of the inner tube on the outside is pi divided by the diameter multiplied by L. Pi multiplied by the diameter is 0.019 multiplied by the length. And that would give us an area of 0.0597 square meters. So let's go and calculate the total resistance now, which is equal to 1 divided by the overall heat transfer coefficient multiplied by the surface area. So 1 divided by, I forgot to mention, this heat transfer coefficient is given as 800. Watts per square meter degree Celsius, and the heat transfer coefficient on the outside is given as 1,200 watts per square meter degree Celsius. Okay, so it is 1 divided by the heat transfer coefficient on the inside is 800 multiplied by the surface area on the inside 0.0471. plus the fouling, which is 0.0004 divided by the surface area is 0.0471. Okay. So 1 divided by the heat transfer coefficient on the inside, the area on the inside, plus the resistance on the inside of fouling, plus the area on the inside, 0.0471, plus the resistance of the wall, which is the ln of the diameters, 0.019, divided by 0.015, the ln of that ratio, divided by 2 pi, k is 15.1, and L is equal to 1. If there's somebody, please, that can maybe check for us the ln of 0.019 divided by the ln of 0.015. It would be nice if you can check quickly for us what it is. Plus, then 1 divided by the heat transfer coefficient on the outside, which is 1,200 multiplied by the area on the inside, the outside 0.0597, plus the fouling is equal to 0.0001 divided by 0.0597. Now most people will take something like that and they would just add it together. I would like to ask you not to do that. I want you to rather write out these terms so that you can look at it. So that is equal to 0.02654 plus 0.00849 plus 0.0025 plus 0.01396 plus 0.00168. Because what is important is the relative sizes of all these components. Okay, so in terms of, if we go and look at the total value, then we will see that this component is contributing 49% to the resistance. The fouling is contributing 16% to the resistance. Did somebody check for us the ln of 0.019 divided by 0.015? Okay, so that is very small, but you'll see that that resistance is 5%. This would be 3%, the other fouling, and then that would contribute to 26%. And this resistance would add up, if we get the total of 0.0532, and the units would be degrees Celsius per watt. Okay, but before we continue with that answer, let's just look at all these components. So in this case, where we've got a tube, inner diameter 15 and outer diameter 19, that is a relatively thick tube. Okay. So you'll see that even if the tube is relatively thick, and this K value of stainless steel of 15, this contribution would be about 5%, so that is very small. But what we have in this case is that the contribution of the overall heat transfer coefficient on the inside is 49%. The fouling already contributed 16%, so that is quite significant. The heat transfer coefficient on the fouling on the outside was just 3%, while the heat transfer coefficient on the outside is 26%. So this is quite a well-balanced problem. You're not going to get this problem on this heat exchanger to have much more heat transfer by changing one of the two surfaces, by adding fins or anything like that. Of course, it's well-balanced. And we are going to do many examples where I'm going to show to you where we do not have a good balance. But in any case, we need to go on with that value there. Let me write here. And remember, 1 divided by the heat transfer coefficient in the inside, area on the inside is 1 divided by the overall heat transfer coefficient, area on the outside, is equal to R. And that R is equal to 0.0532. We're going to work it out just now. The heat transfer coefficient on the inside, the area on the inside, 0.0471, is equal to 1 divided by the heat transfer coefficient on the outside, area on the outside, 0.0597, is equal to the total resistance, which is equal to 0.0532. Okay. And that gives us an overall heat transfer coefficient based on the inside area of 399 watts per square meter degrees Celsius. And the heat transfer coefficient based on the outside area is equal to 315 watts per square meter degrees Celsius. So here we can see a classical case where the two overall heat transfer coefficients are not the same. Why? Because the two areas are not the same, 0.047 and 0.059. However, and that is the important thing, is if we go and check U multiplied by the area on the inside, then that would be equal to 18.79 watts degrees Celsius, and for this case, U multiplied on the outside multiplied by the area on the outside is also 18.79 watts per square meter degrees Celsius. Okay, so although the two U values are not the same, the UAs, the product of the two, will always be exactly the same. And it would be this product that we're going to use to determine the heat transfer rate. Because the heat transfer rate would be equal to UA multiplied by the LMTD, or it would be equal to UA based on the outside LMTD. And we will do examples like that in the next class. Thank you, ladies and gentlemen.